An autonomous vehicle can map the physical geometry of a street with millimeter precision. But if a pedestrian on the curb suddenly glances at their phone and tilts forward, that system is often blind to what happens next. Current perception pipelines rely on a multi-sensor fusion of LiDAR, radar, and cameras to achieve localization accuracy within 5 to 10 centimeters. While standard algorithms like Yellow V8 are highly optimized for drawing bounding boxes and assigning basic labels, they struggle with nuanced semantic granularity. They can identify a pedestrian, but they cannot inherently reason about that pedestrian's intent. This creates a vulnerability in out-of-distribution edge cases. When environmental variables introduce heavy rain, strange lighting, or unusual debris, the lack of higher-level context causes traditional object detection to falter. Navigating a chaotic urban intersection requires interpreting subtle cues, making eye contact, reading pedestrian hesitation, or understanding the unspoken right-of-way among multiple vehicle types. Spatial geometry is the baseline for autonomy, but achieving level 5 requires a secondary layer, contextual reasoning that interprets the data those sensors provide. To bridge this gap, engineers are introducing vision language models and large language models directly into the autonomous architecture. The core mechanism is translation. The system takes raw 3D visual and spatial data and converts it into discrete semantic tokens. Once the physical world is tokenized, the vehicle can apply standard natural language processing techniques to analyze physical spaces, parsing a street corner with the same logic used to parse a sentence. This framework transitions the vehicle's core logic from reactive physical control to predictive context-aware planning. Treating the environment as a comprehensible language allows the FSD agent to interpret road conditions through a logical framework rather than just a geometric one. This diagram outlines a driving LLM agent's architecture, using 3 data transformation phases to convert physical inputs into actionable language prompts. On the left, the vector encoder phase separates environmental inputs, like routes, traffic lights, and pedestrians, into distinct token streams. These raw tokens are fed through multi-layer perceptrons, or MLPs, which compress the disparate data into 32 distinct latent representations. A cross-attention block weights the car's state against external actors' trajectories. In the central vector former, 64 queries use attention mechanisms to synthesize this into a single vector embedding. This mathematical prompt feeds directly into the large language model on the right. To adapt this for driving-specific reasoning, the system uses low-rank adaptation, or LoRa modules. These allow the system to fine-tune responses across query, key, and value matrices without altering the massive base model weights. This pipeline effectively compresses a chaotic, high-resolution 3D world into a highly structured semantic query that the LLM can instantly analyze. An LLM can reason about a scene, but a critical challenge remains. How do we mathematically constrain that reasoning to ensure the car executes safe, human-like driving behavior? This HUG-DRL diagram outlines a framework for behavioral alignment. Environmental state data, like eco-vehicle and pedestrians, feeds into a human supervision module. The control transfer block continuously weighs automated actions against human interventions, shaping the neural network's learning through an experience replay buffer. By combining human supervision with automated evaluation, this approach achieves significantly faster convergence during model training compared to standard reinforcement learning. Embedding human intuition directly into the reward function forces the LLM's semantic capabilities to operate within strict physical safety bounds. Vision language models excel at managing long-horizon navigation goals, but their inclusion introduces an entirely new class of failure modes. The primary vulnerability lies in adversarial perception attacks, where targeted noise is introduced to the physical environment to intentionally deceive the AI. This diagram shows how adversarial noise bypasses standard object localization. The noise directly corrupts the cross-attention layers of the VLM. Instead of parsing a stop sign, the altered attention weights generate a clear-to-accelerate hallucination. This highlights the generalization gap. VLMs suffer performance degradation when exposed to out-of-distribution data that they haven't been explicitly trained to recognize. Because VLMs lack basic spatial common sense without rigorous bimodal supervision, they can be tricked into making confident but incorrect inferences. This is the paradox of the VLM. The architecture that allows the vehicle to reason also makes it susceptible to confident, logically structured, and entirely hallucinated decisions. Deploying these models safely requires a series of engineering countermeasures, starting with continuous closed-loop learning environments. Platforms like LimSim++ force the LLM agent to utilize memory and reflection mechanisms, requiring the system to validate its current choices against historical driving data. Engineers are also implementing domain-specific language, or DSL filters, like the Hudson system, which operate as a firewall between perception and reasoning. These filters logically parse incoming data and reject adversarial anomalies in real time, catching corrupted inputs before they can trigger a hallucination in the main language model. Achieving Level 5 autonomy requires more than just adding sensors or scaling up language models independently. The future of self-driving requires the integration of semantic reasoning with the deterministic safety of control theory.